What's going on, guys? Now we're moving on to section 5.2, okay? And this is about the characteristic equation. So let's get started. Let's move on to example 1. You have find the eigenvalues of A, where A equals this matrix, 2, 3, 3, minus 6. So what you want to do is solve this equation right here, A minus lambda I x equals 0. This is given by ax equals lambda x, which was defined in the definition, okay? Remember that this equation right here is equal to ax equals lambda x, and that was the equation that was defined in the definition, which we thus converted to this form. I hope you still remember that critical fact. So this problem actually threw me off a bit until I had to read carefully this statement. By the invertible matrix theorem in section 2.3, this problem, the problem of finding a lambda that satisfies this equation right here with a non-trivial x as a solution, this problem is equivalent to finding all lambda such that the matrix A minus lambda I is not invertible, okay? So we want to find the values that make this vector right here not invertible. So first we have to find this vector. You put A right here, you put this vector right here, and because we know that there's a diagonal of 1s along the identity matrix with 0s everywhere else, lambda I will basically transform all the 1s on the diagonal into lambdas, okay? So you do the subtraction, you get the matrix right here, and we want to find the values of lambda that make this matrix not invertible. So what do we have to do? Well, we know that when something is not invertible, the determinant is 0. So what we do is we find the determinant and set that equal to 0. Okay, determinant's easy. AB minus BC. You calculate the determinant, you get this quadratic equation right here, lambda squared plus 4 lambda minus 21. You factor, you find that lambda equals 3 and lambda equals 7. Those are the eigenvalues, okay? Then they start talking about determinants, and I don't really understand why, because we already went through this stuff in the other section, right? So when A is not invertible, the determinant is 0. That makes sense, because if you put the matrix into its triangular form, its row echelon form, then at least one of the pivots will be 0 when A is not invertible. And when A is invertible, all you do is you have your minus 1 to the R, and every time you do a row replacement, which the R stands, you have to switch signs, okay? So that's why minus 1 is raised to the R times the product of the pivots in V. And the product of the pivots in V is the numbers along the diagonals in U. It's the diagonals along the U which define the determinant. Compute the determinant A for A. Honestly, I don't think you need to know that. You know how to do that. So now we come to this theorem, the invertible matrix theorem continued. So what this is saying is you have A, n by n matrix. A is invertible if and only if the determinant of, I'm going to start with the second condition first. The determinant of A is not 0. That's correct. We learned that in the beginning. The number 0 is not an eigenvalue of A, which is correct, because in the last video, theorem, I forgot which theorem. Theorem 1. Theorem 1 says that the eigenvalues of a triangular matrix are the entries on its main diagonal. So the number 0 is not an eigenvalue of A. It means that the 0 is not a number along the diagonal of the matrix, which is what makes it invertible. Properties of determinants. Honestly, I think you know what those are, right? A is invertible if and only if the determinant does not equal 0. The determinant of a product is the product of the determinants. The determinant of the transpose is just the same thing as the determinant of A. If it's triangular, the determinant is a product on the diagonals. A row op does nothing. A row interchange changes signs. A scaling multiplies the determinant by scaling. Now we come to the characteristic equation, and I don't want to continue this video. I want to break this video up so that it's short. So I will continue in the next video. Okay? See you soon.